Hi, my name is Kaylin Cummings, and today we're going to be talking about Physics Lab 5, which mine is over collisions. There are many purposes of this lab. One purpose was to gain deeper understanding on the physics models or concepts behind collisions. Another purpose of this lab was to be able to compare and contrast a computational and experimental model concerning collisions. There are many models and principles involved in this lab, consisting of Newton's second law, friction force, conservation of kinetic energy, and determining whether a collision is inelastic or elastic. In the end of the experiment, we noticed both similarities and differences in the computational and experimental models. We were able to determine that energy is moved between system and surroundings, and therefore kinetic energy is not conserved. In that case, we concluded that the experiment's collision was indeed an inelastic collision. Newton's second law, or F net equals mass times acceleration, is involved in this lab as it can relate to many update formulas, including the velocity update formula and the position update formula. These update formulas will be used in our coding to determine a correct pathway for the collision. We will acknowledge the force of friction in this lab. We can get the friction force from the velocity update, seeing as normal force cancels out with the force of gravity. This is because there is no vertical movement present. Therefore, F net is entirely due to friction. As we know, energy is never destroyed or created. Along these lines, we can view the conservation of kinetic energy and the conservation of momentum. The conservation of kinetic energy is resembled by the formula below, stating that K initial is equal to K final. We can also view conservation of momentum, where we can see P initial is equal to P final. We can also view two types of collisions. One type of collision is the elastic collision. This is also known as the bouncy collision. In this collision, kinetic energy and momentum are also conserved. However, in the elastic or the sticky collision, kinetic energy is instead absorbed by the surroundings, while momentum is still conserved. In this experiment, we, as always, have a system and its surroundings. The system consists of the two ping pong balls that end up colliding with each other. The surroundings includes everything else. Here we display the initial conditions. The initial conditions include initial positions, initial velocities, and mass. We were able to receive the initial positions from tracker. The initial position for mass A was 0.132.365 meters, whereas the initial position for mass B was 0.101.0176 meters. We received the initial velocity by completing the following formula, stating that the change in distance divided by the change in time is equal to velocity. We used coordinates that we received from tracker to determine this. For mass A, the initial velocity was negative 5.63 e negative 2, negative 7.9 e negative 1, 0 meters per second, whereas the initial velocity for mass B was 2.31 e negative 2, 7.21 e negative 1, 0 meters per second. We received the value of the mass from Google, stating that each ping pong ball weighed 2.7 grams. Here's the data we used for the initial conditions. The process for this experiment was quite straightforward. First, we recorded our video. Then we analyzed this video via tracker. Then we created a code based off of values from tracker and the internet. And then for the final step, we created models from those codes, and then we compared them. To begin our code, we created the tracker visual using the first component of the coding. After this, in the next section, we created the graphs which we will use to compare values. Following this, we set our initial conditions and values, including mass for each of the balls, which was the same, the position of each of the balls, and the velocities of each of the balls, as we calculated earlier. We also provided the gravity constant, as well as the initial time, which was 0, and the change in delta, or delta t. The t equals t plus delta t section allows us to have values for each timestamp. The two sections below contribute to our visualizations. Here we have our first while loop, which determines values prior to collision. The first two lines show the net force, which is represented only by the force of friction, as discussed earlier. We had to mess around to find the best coefficient of friction, given that we had the time and position estimates of collision from the tracker. We then used the mentioned velocity update formula to determine new velocities after each change in time. This code takes place after the first while loop, but prior to the second while loop, in order to reset the initial conditions after the collision. This is our second while loop. The difference is that this while loop takes place after the collision, whereas the other one takes place prior. This is the first visual that our code produced. Here are the following visuals, or graphs, produced by our code. These represent the change in x and y positions over time by mass A, the red line, and mass B, the cyan line. As you can see, where these lines come close together is where the collision took place. We can compare and contrast the observed tracker model with the predicted computational model. There is further horizontal movement in ball 1 for the observed model, while this was the case for ball 2 in the predicted model. In both models, the balls moved in different y directions upon collision. However, both also moved left afterwards. There were multiple possible errors that could have taken place during this lab. Possible error 1 is misuse of tracker. Possible error 2 is improper adjustment of net force. Possible error 3 is flawed use of Excel. Our first question concerns whether energy is being lost. We can see that there is change in velocities, which is consistently present. This impacts kinetic energy, and its formula being 1/2 mass times the change in velocity squared. Friction here is also doing work. Therefore, we can conclude that energy can be transferred into the surroundings due to friction being present as well as the collision taking place. To determine what type of collision is present, we use this flow chart as shown below. The first question asks whether kinetic energy is conserved, using the formula we discussed earlier, of K initial being set equal to K final. Our answer is no, seeing as these values were not equal with changing velocities. Therefore, this was an inelastic collision. However, we can take this further to say, was this a basic inelastic collision or a perfectly inelastic collision? The types of collisions, elastic, inelastic, and perfectly inelastic, are shown below in the diagram I created. As we can see, the velocity did not become zero in the end. Therefore, it was an inelastic, basic collision.